This section is about estimation, and we never really know a true population, or I should say rarely know a true population parameter. And what do I mean by population parameters? Well, we have the population mean, which is mu. And so because we don't know the true population, what we use are these estimators. And what we use for our 1-point estimator for the population mean is the sample mean, which we call X bar. So because this is estimating, we would like to have some kind of confidence, as they call it, that our population mean is around, at least close by this sample mean, our point estimator. And how we do this is with confidence intervals. And so all confidence intervals is we have, let's just stick with the mean here, we have our population mean here, but then we have some error, okay? And we'd like to have some type of confidence that we fall within this error. And so this in here is our confidence level. And typical values, we like to be 99% confident, 95% confident, and so on. And you might say, well, I want to be 100% confident. Well, it doesn't happen in the real world, right? And a lot of times it depends on what you're doing. If you are building, I don't know, a desk, and you want to make sure that it doesn't wobble and stuff, if you're a little off, on your measurements, may not be a big deal, versus maybe if you're making an incision on somebody's eyeball, gross, right? So, a lot of this confidence level depends on what you're doing, and also sometimes will depend on, are you having to destroy product to get your sample? So if you're landing airplanes and you want to see if they crash, probably can't have a very large sample size, okay? So it can't depend too much on your sample mean. All right, so as I mentioned, these confidence levels typically, and you see them in decimal, 99, 95, and so on. And so what we look up in tables, or we use Excel, is we look up what these are called our critical values. Okay, so these are my critical values. And we need these in our formula to find our error. All right, so we either look these up, and if we're looking at in this case, we're going to look at a population mean where we know the population standard deviation. All right, let's just say it is known. There's historical data, and this is known. Then what we can use here are Z critical values, and this would simply be the negative, and that would be the positive. All right, so as we saw with a normal distribution, we can easily find critical values in a Z table. Also, we can use Excel, as I've showed as well. So the only thing you have to be careful of is when you read the table, and usually the table will show this, that the area that you're finding, and let me just do this, is the area all the way from -infinity up to that value. So the same thing here. And so you have to be careful when, let's say for example, I want a 99% interval. All right, and so that's my 0.99. As we know, all probabilities have to add to 1. So what's in this area and this area right here? Well, wouldn't it be 1 minus 0.01? Right, so 1 minus, I'm sorry, 0.01. 1 minus 0.99, which is 0.01. But there's 2 of these, so we have to divide that by 2. 0.1 divided by 2. So if I was using a table or using Excel, I have to be aware of that. And so let's say that I use Excel, and we've seen this before, the norm dot S dot INV, I actually would plug in that number, which is 0.005, which is your 0.01 divided by 2. I could also plug in 0.995, did I say the points right? Yeah. You know, to get the positive. And because this is symmetric, you will get the same values. So you should get a negative 2.58 and you should get a positive 2.58. All right? So when we conduct these confidence intervals, because I'm going to do one here in a next example, what we do is it's an interval about our mean, and you can see it in the picture there, right? And so how we write this out is our mean is between, our population mean is between our sample data minus some error and then our sample data plus some error. And so what we need to compute is this E, which is our margin of error. So this right here is our margin of error. And you've heard this before, where political polls, somebody's ahead plus or minus 3, right? 3 points or 3%. That's what this is. It's the same thing. And so our formula for this margin of error is simply our critical value that we look up in a table or use Excel. And then if you remember, this was our standard error. And so now we can come up with this error to wrap our interval around our population mean. All right, so now that we see we have a way to compute this error, let's go through an example. So this example says this person, Julia, enjoys jogging, and she has her population standard deviation given here, and we have a random sample. This is important because this is definitely greater than 30, so we can approximate this with a normal distribution. What does that mean? We can use the z-table for our critical values, and then we're given this her mean, sample mean based on her jogs. All right, so if I want to come up with a 95% confidence interval, so again, if you draw this out, what you're trying to find, 95%, are these values right here. Okay, so you're trying to find 95, if I took 100 samples, 95% of them would fall within this interval. And so to do this, writing everything down that is given to me, I see my N is 90. Okay, my sample size is 90. And then I see my standard deviation is 1.80. And for my 95% confidence interval, what's kind of cool, I've shown you, how to look these up in a table, and I've also shown you how to use Excel. Typically online, you could find tables that these are used a lot. Remember I said, usually you see a 99%, a 95%. And so using this, I can see that I'm going to use my critical value of 1.96. And so from here, what I'm going to conduct now is my confidence interval, which is my mean minus my error, and my mean plus my error. And so from here, I have all my information. I just simply plug stuff in. Now you'll see I tend to shortcut this and I write plus or minus. So my mean, which I should have put up here, is 15.6 plus or minus my error, which is my critical value, 1.96, and then my standard error, which is 1.80, divided by the square root of 90. And if I do the minus and I do the plus, I get 15.23 and 15.97 that I can now actually write up here that shows my actual interval. And so again, you can't be 100%, but we can get some type of confidence, okay, of this person, their mean jogging time, based on this information with that margin of error. I remember when I first took statistics, and everything was, is the sample size big enough? If the sample size is big enough, and we even had to go out and do samples and do different types of testing, and as you're actually going to see with hypothesis testing. But I was the one that always asked, how do I know how many samples to get? There's actually a formula for that. If you actually go back and look at the margin of error formula, and if you did the stuff those crazy kids are doing in algebra and you solved this formula for n, that's this. That's the sample size formula. That's all it is, sample size formula. So in this example here, it says we're looking at the mean weight of salmon and how large of a sample should be taken for 99%. So we know n is our sample size, what we're trying to find. My 99%, in fact I can go back here or use Excel, however, I can see that's 2.58 in my table for my critical value. So this is 2.58. They give me the sample standard deviation, so that's all I have here is my sample. And so my sample standard deviation is 2.15. And then my error, they tell me they want within 0.2 tenths of a pound. And so I plug all these values in. If I throw this into my calculator, I get, ooh, that was ugly. I get approximately, what I was trying to write, 769.2. And the rule is no matter, even if this was 7.69.001, the rule is you always round up and get one more sample. So you always round up on sample sizes. All right, so the last example was based on doing our confidence interval if we know the population standard deviation. But what if this is unknown? Well, what you find out, there's the student t-distribution. All my teachers always told me about the Guinness story you'll see in the reading of, sampling beer, and, is a great story, right? But one thing that you get out of this is, notice here the big difference, okay? So we're using our error, okay? So our sample standard deviation divided by the square root of our sample size, and we are going to see that this has something called degrees of freedom. And we need the degrees of freedom to look this up in a t-table. Okay, so we look this up in a t-table, as well as to see with this example down here, of course, as you could probably guess, as your sample size gets larger, I mean, think of it here. You're dividing out the standard deviation, the spread. As the sample size gets larger, your spread, your standard deviation, your margin of error is going to get smaller. So that is very, very important with the t. So if you notice this formula, remember when the population standard deviation was known, we used the z. Kind of sort of remember that? And the only thing that looks different is that, right? And so again, this is the big difference. So if we look at an example here, it says we have this archaeologist discovers 7 fossil skeletons. Reconstruction shows the shoulder height, and we're given this data. Well, we can put this data in Excel as they did, and they give me the mean of this data and the sample standard deviation. I can do these same techniques, okay, based off of this data if I want to find, say, a confidence interval, say 99% again, okay, based on this data. And so here now with my error, this should look familiar. but it's going to be a t critical value, and then my margin of error. Okay, so nothing really changes big in the formula. I mean, this is a big deal, this t-distribution, but you just have to be careful that if you are not given the population standard deviation, which is most of the time, you only have a sample, you have to use the sample standard deviation. And so I can work this out based on these values that they give me. So I have my 46.14 minus my error. I'm going to do a 99%, and I'll mention here how I got this value. And then my standard deviation, 1.19, and then divided by the square root of 1, 2, 3, 4, 5, 6, 7 values. I'm going to write it as, once again, as plus and minus. All right, now to find this t critical value, I need two things. One, I need to know the degrees of freedom. The degrees of freedom is just simply the sample size minus 1. So in this case, the degrees of freedom would be 6. And now I either need Excel or I need a table to look this up. Okay, and so again, you can either find this in a t-table. If you use Excel, you just have to be careful, because what I would type into Excel, INV 0.995, remember the 0.0, how we're getting that middle value, okay? You have to draw them. It's an ugly normal curve, go with it, right? So how am I getting this value right here? 1 minus 0.99 divided by 2, which is the 0.005, and how I'm getting that. But then you have to be careful. It actually now wants your degrees of freedom. Okay, so in this case, my degrees of freedom would equal 6. I will mention the newer Excel actually has the INV 2-tail. And in this case, you put that 0.005 and 6, and you'll get that same value. And so if you throw this in a calculator and you work it out, I get, in this example, I got 44.49 for the low and 47.82 for the upper interval, and which should make sense, right? That is between it. And so this is just how quickly you can get these confidence intervals once you can find that error. I mean, that's the big key. And the error depends on if you know the population standard deviation. If you know the population standard deviation, that was the z critical value. If you do not know it, that's the t critical value. We can also estimate a proportion. Okay, so remember we talked about proportions, the binomial distribution, and you can kind of see with the formula, but I mean the big key is these are all the same. You use a sample plus and minus an error. So in this example here that I'm given, it looks like I have 800 students, and my R of who I believe did not get the flu, did not get the flu. So I can easily find p hat. Remember, p hat is my R divided by my N. So that's 0.75. And remember, q hat is just 1 minus p hat. So 0.25. Remember 1, because all probabilities have to add to 1. And so now this makes it pretty easy. You always want to check, remember the requirements, the n times p and the n times q, and you will see they're both greater than 5. But now easily I can plug all this in now for my error. Now notice that estimating the population proportion actually uses a z. Okay, so it's got nothing to do with standard deviations and such, but so to do this, I simply do the plus and minus. So I do 0.75 plus and minus. Notice I'm just following right above there. My Z, I'm doing this for a 99%, so I'm going to do 2.58. And now I plug in my P hat times my Q hat, oops, and then all divided by my sample size. And I got 0.71, which is surrounded by my population proportion, and 0.79. So I am definitely saying I'm 99% confident that the probability of getting this flu shot will be effective, okay, this proportion of the time. The last thing, just kind of mention, not going to really do an example, is you certainly can find you can certainly find the difference between means and proportions. Same thing where, guess what, you're going to use the sample mean for both, plus and minus and error. So there's no, I'll just say the same thing, but plus, there's no difference with all this, but you'll see here with being able to calculate the error. Now, I don't go into this one that much, and let me make this a little bit bigger so you can see it. I don't go into this one a whole lot, and the reason why, one, you can see it gets really messy calculating this, okay, calculating this error, but also if you add the data analysis to Excel, it will do this very nice and very quickly. Make that bigger as well, and you can see that it has all of these built-in formulas for you to calculate very quickly.